All right, so as we saw in the last problem, finding the change in the entropy of a reaction is something that's quite useful. And so naturally the question is, how do we find this value? And so we'll take a look at finding the entropy of a reaction in its standard state. So if you think back to Chem 101, this little degree symbol here means that it's at its standard state. So in case you're thinking what that means, for a pure gas, it means that has a pressure of 1 atmosphere. For pure solids and liquids, same thing. Solids and liquids. And they're going to be in their most stable form. So as we'll see later on, solids can have multiple stable forms. Stable form, right, under 1 atmosphere, and generally 25 degrees Celsius is generally where it's at. And then if you're talking about a solution, you're assuming it's 1 molar. So, right, what you kind of want to do is think back to Chem 101. And what you guys found in Chem 101 was the enthalpy of formation of a reaction. So it's kind of the same thing here. Again, this delta S of a reaction is going to be equal to the S of the products minus S of the reactants. And we can see that these types of problems are pretty simple. We're just going to pull these from tables and basically subtract the reactants from the products. So in order to kind of think about what the entropy of a system is, we kind of have to have something that's 0 entropy. So we can think about that. So entropy S of a perfect crystal, right? So it's a solid, it's super organized at 0 Kelvin. So there's no temperature, there's no movement. There's only one way to organize that macro state. There's only one micro state, and so the entropy is 0. Right, of a perfect crystal at 0 K. And you think back, S equals K ln W, where W is the number of microstates. If W equals 1, the natural log of 1 is 0. So the entropy is 0. And then as far as what these numbers are, it's super simple. You just pull them from a table. If they're reactants, make them negative. If they're products, make them positive. So can pull numbers from a table. So that would look something like this. So there's a bunch of numbers. So if you're thinking about, okay, I want to know what the delta S of, water melting, since we kind of did that example, right? Water melting. What's this delta S of the reaction? Well, right, so you can think about it this way, products or reactants. I essentially think about it the same way. So here we have solid water. So we need to find that in our table. And solid water would be a bit of a trick question because it's not on this table. So I Googled it, H2O of solid water right here. Go away option. It's going to be annoying. Solid water is 41 joules per mole Kelvin. So we can just pull this number straight from here. Liquid water, we just find liquid water right over here. And then we think about, since this is a reactant, we're not forming it, we're destroying it. So any reactant, you're going to multiply by a negative number. And since both of these coefficients are 1, we're going to multiply both of these numbers by 1, as you'll see. So this is a reactant, so it gets multiplied by -1. So this 41 becomes a -41 joules per mole Kelvin. This is a product over here, so we're just going to multiply this one by 1. Again, if the coefficient was a 2 or something, then we'd multiply by 2, but it's a 1, so we're just going to multiply by 1. It's a product, so we don't flip the sign or anything. You can kind of think of these as standard entropies of formation. It's technically not quite right, but it works for the most part. So solid liquid is 70 joules per mole Kelvin, and then we just sum these two. We just sum these two, and that'll give us our reaction. In this case, it's 29 joules per mole Kelvin. So again, pretty simple type of problem. Just think about the coefficients, multiply it by that coefficient. If it's a reactant, multiply by -1. If it's a product, don't